Hello everybody, in this video we are going to go over the 8 properties of logic in order to help you when you're thinking through truth tables and conditional statements. So the commutative property tells us that the order doesn't matter. So for example, if I was to do 3 plus 4, that's the same as doing 4 plus 3. Same as doing 3 times 4 is the same as doing 4 times 3. Not everything has this. For example, 3 subtract 4 and 4 subtract 3 isn't the same. But the commutative property happens when it doesn't matter. You get the same result if you were to flip them around. So in terms of logic statements, the and or are both commutative. So if you did P and Q, Q and P, they mean the same. P or Q and Q or P mean the same, end up with the same answer. The associative property says that grouping doesn't matter as long as the order and operation are the same. So for example, if I have 3 plus 4 plus 5, and I put brackets around 3 plus 4, or I put brackets around 4 plus 5, I end up with the same answer. In conditional statements, how you group the statements doesn't matter. However, again, the order and the operation have to be the same. So if you move the order of the statements around, so if I switched, the Q and the R around, or I changed these operations, then they would not get the same answer. But as long as the order PQR is the same, and I've used the same connective statements here, then whether I group these or I group these ones does not matter. And that happens with the and the or. The distributive property states that by multiplying the sum of 2 or more numbers, that's the same as multiplying each number individually and adding them together. So for example, if I have 2 bracket 3 plus 5, I can do 3 plus 5 and times it by 2, or I can do 2 times 3 plus 2 times 5, and I'll get the same answer. So I can multiply the 2 through the bracket. That's a distributive property. In terms of conditional statements, conjunction and disjunction are distributive. So if I have P and Q or R, I can do P and Q or P and R. So the or would come in the center and the and would go to each letter. So P and Q or P and R. Or if I have them switched around, P or Q and P or R. Okay, so the conjunction and disjunction are also distributive. Okay, so let's prove this. How do we know this? So I'm taking one of our distributive properties here, and we're going to find a truth table for this and a truth table for this, and their truth tables should be the same. Okay, so if I have P, Q, and R, I'm first going to do Q or R. Okay. Then I'm going to do P and Q or R, and this is what I get. Now if I do it the other way and do P and Q, P and R, and then find or, they're the same. Okay, I get the same answer. So if this is my statement, I can either do it as is, or I can kind of distribute the P and through, and I'd get the same answer in a truth table. Double negatives. Okay, so if we have not P, and then we have a not outside of that, so not P, that equals P. And we can see that in this truth table here, because if I find the not P, I'm essentially flipping the signs. If I'm doing it again, I'm switching the signs back to how they were. So if you have 2 negatives, it does equal just the normal statement. We also have the idempotent property, which says that if it is unchanged in value when multiplied or otherwise operated on by itself. So, for example, if I do P and P or P or P, they both just equal P. So it doesn't change when something is done to itself in terms of the and ors. It just equals itself. De Morgan's law states that the negation of the conjunction of two statements is the disjunction of their negations. What does that mean? That means if I take P and Q, and I'm taking not P and Q, then I can essentially distribute this not through the bracket, but I have to change the sign. So this becomes not P or not Q. Okay, so you can't just distribute this through. If you do, you have to change the sign. So here I can do not P and not Q. Okay, so I can distribute the not through it, but I have to change the sign. Okay, and let's take a look at proving that with the truth table. So if I have P and Q, I'm going to find P and Q and then take the not of that, so switch it. And if I take not P and not Q and find or of those two columns, I also end up with the same result. We also have some identity laws. So tautology is if there is all t's in the final column. So the statement is valid, let's say. All t's are in the final column. Contradiction is if there's all falses in the final column. So it's not only an invalid statement, the statements contradict each other. Okay, so if we have P and T, it's just going to equal P because these are all true. And in order to the and means it has to be true in both. So wherever this is true, it's going to be true. Whether it's false, it's false. So it just ends up getting you P. With contradiction, it has to be or, because contradiction is all falses. And so again, it's only going to be where P is true, then the final result is going to be true. Okay. So if I have an and here, P and C, you're going to end up with all falses, because if you have a false column and I'm looking at and, I'm saying are they both true? Well, they're never both true. So you end up with all falses or C. P or T ends up with T, because what you're saying is where are either of them true? Well, if they're all true in T, then you're going to end up with all true, which is T. Okay? P and not P. Where is it true in P and not P? Well, that's never going to happen. And so you're going to end up with all falses, which is C. And P or not P, where is either of them true? You're going to end up with all trues, so you end up with T. Okay, so looking over this video, these are all the different properties that you can use when analyzing truth tables. And so we're thinking about how can you apply these 8 properties of logic in order to solve these application of logic arguments.